Welcome back, Deep Divers. Today we're taking a plunge into something really fundamental, the physics behind ultrasound.
That's right.
Our mission, basically, is to demystify how sound waves interact with different tissues in the body. And then we'll get into the really clever principles of Doppler ultrasound, which lets us actually see movement. We're drawing our insights today from the Ultrasound Physics Study Guide, Day 4, which is a great source for these core concepts.
Yeah. And what's really fascinating here, I think, is that these aren't just, abstract equations on a page.
Right.
Every single image, every measurement a sonographer makes, it's a direct result of these physical principles. Understanding them gives you those real aha moments.
Yeah.
Where you suddenly realize exactly what's happening under the surface, why an image looks a certain way, or maybe why a measurement is proving tricky to get.
I'm really excited to unpack this. We're going to try and make sure that by the end of this deep dive, these, let's face it, complex physics ideas aren't just understandable, but they actually shed light on how ultrasound works in the real world.
Exactly.
So let's get started.
Let's do it.
Okay, so if you've ever had an ultrasound, you kind of know the waves go into your body and somehow magically they come back with information. But what's actually happening to that sound energy as it travels through all those different materials? Let's kick off with something unavoidable for any sound wave. Attenuation.
Right. Attenuation, it's simply the gradual reduction in the intensity, the strength of the sound wave as it travels through a medium.
Okay.
Think of it kind of like a radio signal getting weaker the further you get from the tower. It's the signal fading out.
The fading signal. Okay.
Yeah.
And that fading, it's not just one single process, is it? What are the different components? How does that reduction actually happen?
You're right. It's not just one thing. There are really three main ways this happens. First, you've got absorption. This is where the ultrasonic energy actually converts into other forms of energy, mostly heat. It's a real energy conversion. A little bit of the sound wave literally warms up the tissue it passes through.
Interesting.
Second, there's reflection. This is probably what most people think of. The acoustic energy redirects. It bounces back towards the transducer, off structures it hits.
Right.
And a special type of reflection.
Right.
From really smooth, mirror-like surfaces, that's called specular reflection.
Specular. Got it.
And finally, there's scattering. This is another way energy is lost from the main beam, where the ultrasound waves get dispersed in lots of different directions. This often happens with rough surfaces or really small structures. They don't just bounce neatly back.
Okay, so absorption converts to heat, reflection bounces back, scattering disperses it. How do we, measure this overall loss? Is there a standard way to quantify how much signal we're actually losing per distance?
Absolutely. We measure this using the attenuation coefficient, expressed in decibels per centimeter, DVCM. Yeah. And it tells us precisely the amount of attenuation, the amount of signal loss that happens for every single centimeter the sound wave travels through a specific type of tissue.
dB per centimeter. Makes sense. And speaking of distance and signal loss, I often hear the term half-value layer thickness, or HVL. That sounds pretty important. What's that telling us?
It is important.
Yeah.
The half-value layer thickness, or HVL, is the specific depth the ultrasound has to travel into a tissue for its intensity to drop to exactly half of its original value.
Yes, okay.
And that half corresponds to a very specific decibel drop.
Yeah.
It's a 93 dB decrease.
93 dB.
Exactly. And it has other names too. Sometimes it's called depth of penetration or half boundary layer.
Yeah.
Its units are just distance, so centimeters.
Okay.
Now, here's a key relationship.
Yeah.
In soft tissue, the HVL actually decreases when the attenuation coefficient increases.
So if the tissue attenuates more strongly per centimeter,
Right.
it takes less distance for the signal to drop by half.
Precisely. Think about it practically. If you're trying to image something deep, like, say, the pancreas or something behind really dense tissue, you're constantly fighting against this HVL.
Yeah.
It means even if the structure's definitely there, the signal might just be too weak by the time it makes the round trip back to the transducer. It might be practically invisible.
Wow.
And that's why choosing the right probe, the right frequency, it's so critical. It's really a constant battle against that signal dying off.
A constant battle that really paints a picture. So HVL tells us about the signal fading out over distance, but what actually determines how much of a signal reflects versus how much transmits when it hits, say, the boundary between muscle and fat? What's the property of the tissue itself doing that?
That brings us to impedance.
Impedance, okay.
Impedance is a characteristic that belongs only to the medium itself. It's not about the wave, it's about the stuff it's traveling through.
Right.
And there's a formula for it. Impedance equals density times propagation speed.
Density times speed. So does that mean, really dense materials where sound travels fast have high impedance? How does that work intuitively?
Well, it's density times speed. So something like bone is very dense, and sound travels relatively fast in it compared to soft tissue. So yes, bone has a very high impedance.
Yeah.
Compare that to, say, air or fat, which have much lower impedances. You can almost think of it like the resistance a swimmer feels. Trying to swim through thick mud, that's high resistance, high impedance. Clear water, much less resistance, lower impedance.
Good analogy.
And this difference in impedance between two tissues at a boundary, that's the absolutely crucial part. Because that difference dictates how much of the sound wave energy will reflect back and how much will continue on or transmit.
Okay, so it's the mismatch in impedance that causes the reflection.
Exactly. Big mismatch, strong reflection. Small mismatch, weak reflection, more transmission.
So when the sound wave hits one of these boundaries, impedance changes, energy takes a fork in the road. How do we describe those two paths?
We talk about reflected intensity and transmitted intensity. Reflected intensity is the portion of the energy that changes direction after hitting the boundary.
Right.
And ideally heads back towards our transducer. That's what forms the image.
Right.
Transmitted intensity is the portion that keeps going, more or less in the same general direction after hitting the boundary, traveling deeper into the body.
And are both measured in the same units.
Yeah, both are intensities,
Right.
so they're measured in watts per square centimeter, WCM all three.
Okay. And does the angle the sound hits the boundary matter, or is it always the same split regardless of how it hits?
Oh, the angle makes a huge difference. We talk about normal incidences when the sound wave hits the boundary straight on at a perfect right angle, 90 degrees.
Perpendicular.
Exactly. That's the ideal situation for getting strong reflections directly back to the transducer.
Makes sense.
Then you have oblique incidence, which is basically any angle other than 90 degrees.
Oh.
Now, with oblique incidence, things get more complicated. Physics tells us that transmission and reflection might happen or might not, depending on the angle and the impedance mismatch. It's complex. But when reflection does occur at an oblique angle, a key rule applies. The angle of reflection equals the angle of incidence, like bouncing a ball off a wall.
Angle in equals angle out.
Precisely. And remember those specular reflections from smooth surfaces? They're very angle dependent. If you hit a smooth surface obliquely, that reflection might bounce off completely away from your transducer.
Yeah, so you wouldn't see it.
You wouldn't see it or it would look very weak. This is why, practically, the angle the ultrasound beam hits a structure is fundamental to the image quality. Just a tiny tilt of the probe can make a blood vessel wall, for instance, appear bright or disappear completely.
Wow, okay. That angle is critical. So, we've covered sound hitting a boundary, bouncing off reflection, straight on or at an angle. But what about the sound that doesn't bounce back? The transmitted part? What happens to the energy that passes through the boundary into the next tissue type, especially if it hits at an angle?
Right. That brings us to another key phenomenon called refraction.
Refraction.
Refraction is the bending, the change in direction of the ultrasound wave as it passes from one medium into another.
Yeah.
If those two media have different propagation speeds.
So it bends if the speed changes.
Correct. Think of light bending through a prism, or maybe a straw looking bent in a glass of water.
Yeah.
Or even, like, imagine a toy car rolling from a smooth floor onto a patch of carpet at an angle. One wheel hits the carpet first, slows down, the car turns.
Okay. Yeah, I get that.
It's the same idea with sound waves. The physics describing how much this bending happens is governed by Snell's law.
Snell's law. Sounds important.
It is. We don't need to get lost in the trigonometry, but the core idea is that the amount the wave bends depends on two things. The angle it hits the boundary, the incident angle, and the ratio of the sound propagation speeds in the two different media.
Okay, the ratio of the speeds. Can you give us a couple of scenarios maybe to illustrate how Snell's law works out?
Sure. Let's think about two main cases based on those speeds. Scenario one. If the propagation speed in the second medium, the one the wave is entering, is faster than the speed in the first medium,
Okay, speeding up.
then the transmission angle, the angle the wave continues at, will be greater than the incident angle. The wave bends away from the normal, that perpendicular line.
Bends away, got it.
Scenario two. If the propagation speed in the second medium is slower than in the first,
Slowing down.
then the transmission angle will be less than the incident angle. The wave bends towards the normal.
Bends towards, okay. Why does this matter for imaging?
It matters because this bending, refraction, can cause artifacts in ultrasound images. It can make structures appear in the wrong place, slightly shifted or distorted. It's called misregistration.
Ah.
So understanding that refraction can happen and why is really key for accurate interpretation and avoiding potential misdiagnoses. You have to account for that potential bending.
That's a really crucial point. Okay, we've spent a good chunk of time on how sound travels and interacts with things that are, well, sitting still.
Mm-hmm.
But what if the thing the sound hits is moving? This is where ultrasound gets really dynamic, right? Letting us see things like blood flow or heart valves opening and closing. That's all thanks to the Doppler effect, isn't it? How do we even start to see movement with sound?
Yeah, the Doppler effect is the key.
Yeah.
Fundamentally, the Doppler effect is a change in frequency that happens because of motion.
A change in frequency.
Yes. When the sound source, or in our case, the reflector, like red blood cells moving in a vessel, is moving relative to the transducer, the frequency of the sound wave that comes back is slightly different from the frequency that was sent out.
Okay.
That difference in frequency, we call it the Doppler shift, is directly proportional to the velocity of whatever's moving.
Yeah.
Faster movement, bigger shift. Slower movement, smaller shift.
So that Doppler shift, that change in frequency, that's what actually lets us measure how fast something is moving.
Exactly.
And I know the angle comes back into play here in a big way. I remember seeing the formula, velocity measured equals true velocity times the cosine of the angle.
That's the one.
Wait a minute, cosine angle? Doesn't cosine go to 0 at 90 degrees?
It does indeed.
So if the ultrasound beam is exactly perpendicular to the direction the blood is flowing, the measured velocity is 0, even if it's moving really fast.
Precisely. That's a huge practical point. The angle is absolutely critical for accurate Doppler measurements. Let's break down those key angles. At 0 degrees or 180 degrees, meaning the beam is perfectly aligned with the flow, either heading straight towards the transducer or straight away.
Parallel to flow.
Right, parallel. In that case, the cosine of the angle is 1. Or -1 for 180 degrees. So the measured velocity equals the true velocity. That's your ideal scenario for getting the most accurate speed.
The best case.
The best case. But at 90 degrees, exactly perpendicular, the cosine is 0. And 0 times anything is 0. So the measured velocity is 0 no matter how fast the blood is actually flowing. You get absolutely no Doppler shift.
So a sonographer trying to check for, say, a blockage or slow flow, they have to avoid that 90-degree angle.
They absolutely do. They're constantly adjusting the probe angle, sometimes just slightly heel-toeing or rocking it to make sure they have some angle relative to the flow, ideally less than 60 degrees for good accuracy. If they hit 90 degrees, they might completely miss significant flow or think there's no flow when there actually is. It could lead to a major misdiagnosis.
That makes perfect sense why getting the angle right is so crucial. Okay, so we have this Doppler principle. How is it actually put into practice? What are the different kinds of Doppler ultrasound technologies we find in the machines?
There are two main types, fundamentally. First, there's continuous wave Doppler, or CW Doppler.
Continuous wave.
This type uses two separate crystals in the transducer. One that continuously sends out ultrasound energy, and another one right next to it that continuously receives the returning echoes.
Two crystals, always on.
Always on. If duty factor is 1.0, meaning it's transmitting 100% of the time. Now, the big advantage of CW Doppler is its ability to measure very, very high velocities accurately. There's basically no upper limit to the speed it can detect.
Okay, good for high speeds.
Exactly. Think about really fast, turbulent blood flow shooting through a narrowed heart valve. CW is great for that. However, it has a major limitation. Range ambiguity.
Range ambiguity, meaning?
Meaning, because it's constantly sending and receiving along the entire beam path, the echoes it picks up could be coming from anywhere along that line. You know that there's fast flow somewhere in the beam, but you don't know exactly where, at what depth it's located.
So you lose the location information.
You lose the precise depth information, yes.
Okay, so continuous wave gives you speed, but not specific location. What's the alternative then, especially if you need to know exactly where the flow you're measuring is happening?
The alternative is pulsed wave Doppler, or PW Doppler.
Pulsed wave.
This type uses just a single crystal in the transducer, which alternates between sending out a short pulse of ultrasound and then listening for the returning echoes.
Sending and listening back and forth.
Exactly. And the huge advantage here is range resolution. Because it only listens during a specific time window after sending the pulse, the echoes it analyzes come only from a very specific small region along the beam path.
A specific spot.
Yes, and that spot is called the sample volume, or sometimes the sample gate. And the best part is the sonographer gets to choose exactly where to place this sample volume.
So you can pinpoint the vessel you want to check.
Precisely. You can put that sample volume right in the middle of a specific artery or vein and measure the flow just at that spot.
That sounds much better for localization. Is there a downside?
There is. The trade-off with pulsed wave Doppler is that it's unable to measure very high velocities correctly. There's an upper limit, and if the blood flow velocity exceeds that limit, you get a phenomenon called aliasing.
Aliasing. What's that look like?
It's kind of like watching a wagon wheel in an old movie spinning so fast it looks like it's going backwards.
Yeah.
That's aliasing. In Doppler ultrasound, it means that very fast blood flow might wrap around and be displayed as if it's flowing in the opposite direction, or it might just show up as a garbled mess or an incorrectly low speed.
Ah, so it can fool you.
It can definitely mislead you if you're not aware of it. So you really see this fundamental trade-off, right? CW Doppler, great for high speeds, poor location. PW Doppler, great for precise location, but limited by aliasing at high speeds. The choice depends entirely on the clinical question you're trying to answer.
Speed versus location, a classic trade-off.
It really is. And just to tie things together a bit, many modern ultrasound machines are DUPLX machines.
Duplex.
Meaning they can display both the grayscale anatomical image, the B-mode image, and the Doppler information, either CW or PW, simultaneously, often overlaid on the image.
Oh, that's fantastic. So you see the structure and the flow within it at the same time.
Exactly. It gives you that comprehensive view, the anatomical context from the image and the dynamic flow information from the Doppler, all integrated together. It's incredibly powerful.
Wow. We have definitely covered some amazing ground today. It's kind of mind-bending when you think about it. From the really intricate ways sound interacts with tissue, thinking about how signals fade with attenuation, how differences in tissue impedance cause reflections and let some sound transmit through, and even how waves can bend with refraction. All the way to the super clever use of the Doppler effect to actually measure movement inside the body. It's pretty remarkable how these basic physics principles underpin everything we see on the screen.
It really is. And this deep dive into the physics, it isn't just, academic theory. It is the absolute foundation of every single medical image and every velocity measurement that ultrasound provides.
Right.
It's what allows clinicians to make incredibly precise diagnoses, to monitor conditions over time. It literally lets them see inside the body in ways that were unimaginable not that long ago. Understanding these core concepts, I think, really empowers you, the listener, to better appreciate the true diagnostic power of this technology.
Absolutely. So maybe a final thought for you all to ponder as we wrap up. How does our ever-increasing understanding of these really subtle physical interactions keep pushing the boundaries of what medical ultrasound can show us about the human body? And maybe more excitingly, what new insights, what new diagnostic capabilities might we unlock by learning to manipulate these fundamental principles even more precisely in the future? It really makes you wonder what else we might be able to see down the road.
It's a fascinating question. Knowing this foundation helps you appreciate not just where we are, but also where this amazing technology might be heading.